Got it. All right. So we are looking at the mean value theorem. Our raccoon here prefers the nice value theorem. Of course, we do mean like average. All right, so we've got a particular little doodle here. Oh, while I'm thinking about it, I haven't even started grading the tests yet. My plan is to do that a little bit tonight and then tomorrow. Hopefully y'all's will grade faster than my pre-cal. My pre-cal students had an average of a 60. But they also like just one of the questions I didn't cover it well enough in class, so that's more on me than them. All right, so average rate of change. So what is the average rate of change of this function between x1 and x2? All right, well, what do we remember average rate of change means? Slope, which we know is also a keyword for derivative. All right, so the slope between those 2 points, the instantaneous slope does all sorts of stuff. But when we talk about the average, that's just straight the slope between the 2 points. Oh, look at that. It was a reasonably straight line. All right, so if I look, that goes up 1, 2, 3, 4, and then it goes over 1, 2, 3, 4. Yeah. So that is a not to square scale graph because you can see the grid is a bunch of rectangles. But our slope here was 4 over 4, which was 1. Okay. And now they're saying, what's the equation of the secant line? Okay, fine. Well, we just figured out the slope was 1, so y minus, well, now I actually need an ordered pair point. So this one is 1, 2, 3. Huh? So we could do 3 and 4 over here. This is 7 and 8. Yep, so y minus 8 equals 1 times x minus 7. And we can even see, actually, if we sneak and look, yeah, it's intersecting at 1. So x minus 7 plus 8, y equals 1, x plus 1. All right. Secant line here, secant just means it hits in more than one point, as opposed to tangent line. Okay. Now, how do we find the equation of the tangent line of this function at x equals 3? So if we had the equation, we could take the derivative, plug in the number, calculate it out, or we could do our long definition, the limit as the y's change over the x's. Is that going to be anything like our secant line here, though? Well, like the blue line here is our tangent line. That's got a negative slope, right? And our current secant line has a positive slope. So this was not actually find it. This was just a how do we find it? We'd take a derivative, plug in the number. Is it going to be the same? No. So we ask a slightly different question. Is there anywhere on the graph where the slope of the tangent line looks like it would be equal to the slope of the secant line? Ugh. Hold on, let me flip the share. So Chris actually had this in a Desmos. Yeah, okay. Now what I don't know is where he put, what do we have in here? So yeah, slope is 1. There's our secant line. All right, so I've made a random point here, A, that I can slide around. Because the question is between 3, x equals 3 and x equals 7. Is there a point in there that is going to have a tangent slope the same as that secant slope? So you can think of it like, if I hold that angle and then I grab that whole line and kind of sweep it so the slope stays the same, is there a spot where I can stop it and it's only going to touch the curve in one spot? Now what we have here is we have the slider between all the points from 3 and then whoop, and then all the way up to 7. So we're just kind of looking in there. Is there a spot in there where the slopes are the same? All right. So I got an uphill slope over here, right? Past 6. And if I go back to 4, I got a downhill slope. So does it make sense? Somewhere in there, it should be the same as that slope of 1. Now, it may be hard to pinpoint exactly where that point is, but I can definitely see it sweeping through negative up to much steeper values. So somewhere in there, there should be a point. And seeing that it's kind of like half-ish way between 3 and 7, like it's not exactly half, that would be 5.
Okay, you're good.
So that's how that kind of plays about. So is there anywhere on the graph where the slope of the tangent line looks like it would be equal to the slope of the secant line? Yes. Somewhere around here. My drawing is bad, but somewhere in there it should be equal. That idea is the mean value theorem. So if I pick any 2 points on a curve, I calculate the slope between those 2 points, somewhere between the 2 points is a place where the tangent slope is going to be equal to that secant slope. Of course, we are assuming continuity here. So if this graph had any sort of sharp corners, well, yeah. Or if it had any breaks, a break is where it can really screw up this theorem. So let f be continuous over the closed interval, and differentiable over the open interval. So the differentiable means we don't have any corners. Then there exists at least one point C in AB such that f prime of C equals the slope of the secant line. So as long as the function's derivative exists on the interval, then there will always be a point somewhere in that interval where the slope at that point, the slope of the tangent line, is equal to the slope of the secant line, which is the slope of the endpoints of the interval. Now, there could be more than one, but the mean value theorem guarantees us that there is at least one. So our little example here, find the values of C in the conclusion of the mean value theorem for the given function over the given interval. All right, so doing the whole mean value theorem means we need to find the slope of the secant line. And to do that, I need to find the coordinates of the 2 points, the endpoints. So our interval is given here. That's our from 0 to 8. All right, so my first x value is 0. My second x value is 8. I want to know the associated function values. Well, 0 is at least easy to calculate. That's -20. F of x2, though, 8 is uglier. This is why we have calculators, because sheesh, it's going to be ridiculous. All right, so 8 times 8 to the third power minus 2 times 8 minus 20. And right, obviously that's 4,060. That's ridiculous. All right, now our slope there, y2, 4060, minus y1, -20, over 8 minus 0. So we end up with 4060 plus 20. And then we divide that by 8, and oh wow, it actually works out nicely to 510. So we got like a point and then a ridiculously high point, so our slope is ridiculously huge. But somewhere in between 0 and 8, there's at least one x value that's going to have that same 510 slope as the slope of the tangent line. So I want to find C such that f prime of C equals 510. Like that's the more algebraic way to write what they're asking. So I need my derivative. So I have y. I'm just going to shift it back to function notation. So f prime of x, 8x cubed, so that'll be 8 times the derivative of x cubed. We bring the 3 down. X, 3 minus 1 is 2. So 8 times 3x squared minus 2 times the derivative of x is 1. And then the derivative of a constant, flat line, slope of 0. So I'm not even going to write it. All right, so our derivative is 24 things squared minus 2. I'm going to go ahead and put the c's in there instead of the x. And now I'm going to put 510 instead of f prime of c. So we're going to solve this ridiculous equation. Now, the good news is, even though it's a quadratic, there's no c term, so we don't have to factor this. I'm going to add the 2 over. So we get 512, and then we'll divide that by 24. And forgive me a second. Okay. Equals 24c squared divided by 24. So this is 64 thirds equals c squared. We square root, and we have that plus or minus question. So c is plus or minus this raised to the 0.5 4.6188. All right, so I have a C value. I have two of them actually. But we check over the given intervals. So we're not going to use the negative value because we're only looking at the numbers from 0 to 8. So the value between 0 and 8 is the 4.6188. So we're ignoring the negative number because it's not in our provided interval from 0 to 8. So the mean value theorem itself, in the big picture, I'm going to prove calculus, this theorem is important. Its actual use in application problems, not as much. Looks like we just got more of the same, and a summary. Okay. Eventually, the way we use this is if I pick 2 points that are on the same horizontal line, the slope between them is 0, which means somewhere in between there, I have to have a point that has a 0 slope. So that point would either be a max or a min. That one actually gets called Rolle's theorem, which we didn't even talk about, but that's like the main conclusion of the mean value theorem is if you're looking at a function and you have x-intercepts, those are all on a horizontal line, then in between each of the intercepts, you should see a max or a min. Because the derivative is our formula for the slope of the tangent line at any number. So we're looking from 0 to 1, which here, let's go ahead and do our x1 is 0, x2 is 1. F of x1 is the sine of 0, which is 0. And then f of x2 is the sine of pi times 1, which is the sine of pi, which is also 0. So that pi being multiplied onto the x is messing with the period. So instead of the period taking 2 pi units, now this one only has a period of 2 units. So when we're looking from 0 to 1, we're looking at exactly half a period. So it's the top arc of a sine graph. So our slope of the tangent line over here is going to be 0 minus 0 over 1 minus 0. So we're looking for a point on this graph that's going to have a slope of 0. 0 slopes are where the graph is changing from increasing to decreasing or from decreasing to increasing. So now to find this, I need my derivative. So just going to call this f of x again. So f prime of x. How do we do the derivative of this? So I have sine of pi x. This is creating an outside inside, so it's going to be a chain rule. So what's my derivative of sine? Yep. So I have cosine of the same ugly mess, pi x. And then we do times, what's the derivative of pi times x? Our pi is a constant. What's the derivative of x? Yep, just 1. So f prime of c, I'm just going to rearrange this pi that's outside. I'm going to write it up front. So we have pi cosine pi x. And my slope I figured out was 0. So we have 0 equals pi times cosine of pi x. Get rid of the pi. So I'm now looking at when is cosine 0? So I'll give you all a sec to think while I put some extra space in there. So like my algebraic next step would be to apply an inverse cosine. And if I type inverse cosine is 0 on the calculator, it's going to tell me 90 degrees, which is pi over 2. So my pi x could be pi over 2. Or plus some 2 pi k coterminal angle. The other spot on the cosine graph that has a slope of 0 is the low point. So our pi over 2 is the high point. Our low point is at 3 pi over 2. Now you usually don't need the 2 pi k stuff, so if you forget it here, like you'll still get the answer. This is just one of those, like, technically it applies. You could get this in the calculator. But you have to know there's a second value and how to find it. So you really only need to know quadrant 1. This is the extra bit is knowing the extreme points. So cosine is 0, like it starts up at 1, then it goes to 0, down to -1, back up to 0. So if we're thinking about just our graph, so we have 0 to 2 pi. So our halfway mark is pi. Half of that again is our pi over 2. And then over here, halfway between is 3/2 of pi. So I mean, like, I could think through on the unit circle, but then I'm having to constantly remember, am I looking at the x or the y? And it like boggles my brain. So then I realized, well, if I just remember the shape of the graph, then I can just use the extreme points to figure out. Now, to get x by itself, though, we have to divide everything by pi, which includes the 2 pi k. So now my x could be 1/2 plus 2k, or my x could be 3/2 plus 2k. And on all of these, the k is, let me just type it. Where k is any integer. So our classic case, k is 0. I have x equals 1/2, x equals 3/2. If I put k equals 1, 2.5, that's going to be way bigger than our interval, because remember, our interval was really small here. It was only 0 to 1. So even 3/2 is too big. Yep. So 1/2 is the only value that satisfies the conclusion of the mean value theorem. But there is technically, if I put in like k equals -1, 3/2 minus 2 would be -1/2, or I could get -3/2. Like there's an infinite number of places on the graph where we're going to have a slope of 0, but there's only one point between 0 and 1. The theorem guarantees there's at least one. If I did the interval from 0 to 2 instead, then both of these would satisfy the theorem. But the f of 2 would work out to 0 again. So I'd still have that flat line because I'm just looking at x-intercepts.
And it would also like, did you say you can get in the calculator the 1/2 or the pi over 2, right?
Yeah.
Would that also be like a hint to add like, oh, the other one, you still need to find another one, but they would hit, okay.
Yeah. So if it gave you like pi over 3, then you have to think about, am I looking at sine or cosine? Is it positive or negative to figure out, like if it's pi over 3 and you're looking at sine, then the other one is probably 2 pi over 3. So like whatever the denominator is in the fraction you get, usually the other one you have to solve for has the same denominator. And what that has to do with is the way the fractions work, the reference angle is the denominator. So like pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 all have a pi over 3, which is a 60-degree reference angle.
So you don't really need it. Get the calculator
Mhm.
to find the other point. Okay, then that's the theorem.
Now we don't, well, we're doing plenty good on time. All right, so now this one, they gave us a natural log. And I'll be honest, like when I first looked at this, I was like, from -1/2, we can't put no negatives in a log. And then I looked at it and I was like, oh, okay, I guess we can. So it ain't gonna be pretty, but it's a natural log, so we knew it was gonna be ugly decimals. Ugh, all right. So -1/2 to 7/2. So f of x1 is the natural log of 4 times -1/2 plus 6. So -2 plus 6, this is the natural log of 4. And then over here, 4 times 7/2, which is 14 plus 6 is the natural log of 20. All right, we are going to have to use some log rules in here. So we have the natural log of 20 minus the natural log of 4, and that 2 looks like a 1, over 7/2 minus -1/2. So that's 8/2, so that's 4 on the bottom. And then the natural log of a number minus the natural log of another number, I can actually combine those into a single log. So it becomes the natural log of 20 over 4. So we have the natural log of 5, and then that's divided by 4, or you could write it as 1/4 the natural log of 5. So now we want to find the value in the function whose derivative will equal natural log of 5 over 4. Now I'm leaving it like this, like we could do it with the decimal. But then there's like this, like, but we're rounding. And I don't know how anal web work is going to be on these. All right, so either way, we definitely need our derivative. So mathematicians have an unhealthy obsession with exact values. To a mathematician, natural log of 5 over 4 is an exact value. To type it in the calculator and write down the decimal is an approximation. It's not the same. Because it is ever so slightly off based on where you stop writing the decimals. Like realistically, if you're doing any sort of application with this, like you could carry a bunch of decimal places if you're doing like something that requires that degree of accuracy, but there is a point where the numbers afterwards won't have that big an impact anymore. But to a mathematician, no, it's the natural log of 5/4. Yeah, like to them, it's the square root of 3. It's not 1.73. No, it's the square root of 3. So math problems, if they're not programmed with a tolerance in the answer, then if you typed in a decimal approximation here, it could be like, no, I don't like your answer because the person who programmed me was an asshole.
It's kind of like what happened with the fraction. When I tried putting like 5/2 and the like. Or no, I kept putting the 1/4 and I'm like, no, I decided to put like 5/2.
It could be. They just, WebWork gets stupid sometimes. All right, so we need our derivative. So doing the derivative of a natural log. Not as nice as our e to the x, but close. So we get 1 over whatever we're taking the natural log of. And then times the derivative of what was inside the natural log. So the derivative of 4x plus 6. So the derivative of 4x would be 4 times 1, x to the 0 is 1. And then plus the derivative of 6 is just 0. So I got that whole thing times 4. And this could reduce, but remember we have that like over 4 over here. So I think maybe it'll work out a little, maybe not. I don't know. We'll see what happens. All right, so 1/4 the natural log of 5 equals 4 over 4x plus 6. Yeah, I'm just gonna put that back to over 4. So we can cross multiply. So I have the natural log of 5, which is some ugly number, times 4x plus 6 equals 4 times 4 is 16. I could distribute the natural log 5 through, but we don't really have a lot of rules for proper notation on natural logs, so I'm just going to divide by it now. So 4x plus 6 equals this weird 16 over the natural log of 5. We will minus the 6. And then we will divide by 4. And there is our x value. If we're leaving it all pretty in mathematician form, if you will. Most of the WebWork problems are actually programmed to accept a decimal. That's why we tell you guys to write 4 or 5 decimal places. So we could have actually just done the natural log of 5 divided by 4, written the decimal, and just solved this with the decimal, and you would have been fine on WebWork. I'm just not 100% sure because I haven't actually dug into the WebWork yet for this. But now is as good a time as any. 3. Hate it when they're short. Because I have this like half moment of like, yes, only 3, and then wait a minute. How long are they gonna be? All right, so the first one is a cubic function with some endpoints, so it's very much like the first example. The second example is the sine of pi x we did. It's just the endpoint values are different. And we'll get multiple c values. And then the third one is a natural log function where the inside is slightly different and the numbers for the interval are ugly. Like here, let me snapshot it and show you. So it is almost identical. The interval numbers are a little uglier. I believe that's a 26 over 5. Because if it was 25 over 5, they'd just write 5. The way we type in the answers, though, apparently has to be C equals a number, comma, C equals a different number. I don't know if there'll be, in fact, there likely isn't more than one on the natural log, but on question 2 with the sign graph, there should be several, depending on how wide the interval is. But they should all end up being like half values.
Who's gonna have that decimal point? Or because they write it like that, it shouldn't be.
So if you solve the answer so it looks like this crap, it should take it or I'll kick it. But you could probably just do the decimal for what we got as the slope, the natural log of 5 over 4. Solve this with the decimal there instead. As long as you're carrying like 4 or 5 decimal places through your calculation, it should work. Like, I'd be shocked if it didn't. I just haven't had the time to play with it to know if this is one of the ones that's like super anal. Usually they're not, but every once in a while one sneaks in. So related rates is due today. Are there any questions on the related rates homework that you'd like me to tackle? Because we do have a little bit of time, so I could do that. In related rates? So 4.1 related rates, problem 3. Hold on. All right, so we're looking at dz dt. And first they want us to do it either using with the primes or with the like, you know, d whatever dt notation.
Plus dy dt times y all over the square root of x squared plus y squared.
Did you try typing all over z
Yes.
and it didn't take it? But it took it when you did the square root? Okay. All right, well, that is the derivative, so I don't know why it's being obnoxious. So like it'd be 2z dz dt equals, when you put z down there. I mean, the problem with the square root is it's the plus or minus, so if you just say z, it takes the plus or minus part out of it, but it should have taken it either way. It's just being obnoxious. So that's our derivative, and then we would divide by the 2z. So all the 2's cancel out. So I would write it like x times dx dt. It shouldn't care, but that is the like more conventional notation, is to put whatever d whatever dt at the very end. And then they've given us dx, dt, dy, dt, x and y. We'll have to put x and y back up here to figure out z, but then we have our thing. But yeah, sorry, this is dz dt. All right. I think we tackled the rest. Like in the examples we did for related rates pretty much. I do have my office hours. Any last minute questions? All right, let me cut off the recording.